In this video, we will learn how to solve polynomial inequalities, and we will learn how to determine if a polynomial is even, odd, or neither. This is AP Pre-Calculus Topic 1.5. If you appreciate the channel, please don't forget to hit that like button. Quick reminder, when we write f of x, we are referring to the y value on the graph of f of x. So f of x greater than 0 means the graph of f of x is above the x-axis. And when f of x is less than 0, that means the graph is below the x-axis. So where does f of x equal 0? That's going to be on the x-axis, which is at x equals -3, x equals -1, and x equals +3 in this case. Where is f of x greater than 0? In other words, where is f of x above the x-axis? That's going to be on this interval and this interval. So we're going to say between -3 and -1. In interval notation, that would look like this, from -3 to -1. Union x is greater than 3. Or we could say 3 to infinity, sticking with interval notation. Where is f of x less than or equal to 0? Well, let's see, less than or equal to 0. So less than 0 is going to be here. Whoops, straightened out for me. I'm just going to leave it. But the equal to means I'm going to include the endpoint. And then this portion of the graph that's below the x-axis, all right, from here to here. But again, because of the equal to 0, we're going to include the endpoints. So when I didn't have the equal to sign, I used parentheses to show that I was not including the endpoints. Now I'm going to need brackets. So this first interval is from -infinity to -3, bracket. And then union -1 to 3 with brackets. Here are the steps for solving polynomial inequalities. That means with a greater than or less than sign or less than or equal to, etc. Step 1 is to set f of x equal to 0 and solve. Then we are going to create a sign chart using the solutions from step 1. And then we're going to use test values in each interval to see whether the function is positive or negative in each interval. Then we interpret the sign chart to answer the given inequality from the problem. Be sure to pay careful attention to the endpoints. If we have a greater than sign, like this, then we're going to use parentheses to show that the endpoints are not included. When we have a greater than or equal to sign, or less than or equal to, then we're going to use a bracket to show that the endpoints will be included. We will refer to this part of the inequality as f of x. So step 1 is to find out where f of x is equal to 0. And I encourage you to label your work just like I'm doing. We can do this at a glance since they were kind enough to give us the polynomial in factored form. F of x will equal 0 at x equals 3, x equals -1, and at x equals -4. Now we need to make a sign chart using these solutions. Label your sign chart as f of x in the upper left-hand corner. You're going to need a row for every factor. So I need a row for x minus 3, a row for x plus 1, and a row for x plus 4. Each one of these lines represents a 0. you need to treat this as a number line and put these in order from left to right. So I need to start with -4, and then I have my -1, and then the 3. Now you ask yourself whether each factor is positive or negative in each interval. So looking at x minus 3, it helps to remember which one of these zeros came from this factor. So x minus 3 gave us the factor, gave us the 0 of 3. That's important because this factor will only change signs at 3. So to the left of 3, this factor is going to be negative. To the right of 3, this factor is going to be positive. Okay? For example, 0. If I plugged in 0 for x, that's -3. So to the left, it's negative. To the right is positive. X plus 1 gave us a factor of -1. This factor will be negative to the left and positive to the right. X plus 4 gave us a factor of -4. It will be negative to the left and positive to the right. On the top row, we consider the overall sign of f of x. We can really just count the negatives. If we have an odd number of negatives, then the function will be negative. If it's an even number of negatives, the function will be positive in that interval. So in this first interval, I see 3 minus signs, so f of x will be negative there. In the next interval, there are 2 negatives, so that makes a positive. A negative times a negative is positive. 1 negative, that's odd, so f of x will be negative. And then, of course, all positives, f of x will be positive in this interval. So we can focus on this top row to answer the question. So the question is, where is f of x greater than 0? So the solutions are going to be where f of x is positive. So that's going to be in this interval and this interval. Please remember that since we have greater than 0, not greater than or equal to 0, we will use parentheses and not brackets to show that the endpoints are not included in this. So f of x will be positive and thus greater than 0 on the interval from -4 to -1, union the interval from 3 to infinity. So that's how you solve a polynomial inequality. I encourage you to pause the video and try this one by yourself. I'm going to assume that you just did that. So we start by finding where f of x is equal to 0. Again, this is in factored form, so we can see that that's going to happen at x equals -2 and x equals 5. Now, time to make the sign chart. Your sign chart should look like this. We have 2 factors, so we have 2 rows. Make sure you include the exponent on the factor of x plus 2 squared. That's very important because since this factor is squared, it is going to be positive no matter what. All right? Because even if you have a negative value, once you square it, it turns positive. Now, the x minus 5 gave us the 0 of 5. This factor is going to be negative to the left and positive to the right of that 0. The overall sign of f of x is negative in the first interval because of the 1 negative, negative in the second interval, and of course positive in the third interval. F of x is less than 0 in these 2 intervals because of the negative. And because we want to include any values where f of x is equal to 0, less than or equal to 0, we will use brackets as we write the final answer. Since our solution consists of 2 consecutive intervals, including the number in the middle thanks to the or equal to sign, we can write the solution as a single interval. This interval goes from -infinity to 5. Don't forget to put a bracket on it because of the or equal to include the 5. So that's the final answer. By the way, I like interval notation, but if this were a multiple choice question or something, you might see the answer represented as x is less than or equal to 5. Everything to the left of and including 5. So be able to recognize that as an answer. Similarly, the solution from example 4 could be expressed as an inequality like this. Now I will teach you how to determine the degree of a polynomial given a table of values. If given a table of values with equal input intervals, we can determine the degree of a polynomial by examining successive differences in the output values. The number of successive differences needed for the differences to be constant is equal to the degree of the polynomial. Here are the first differences in the output values. They are not the same yet, so we need to find the differences between these differences. These are the second differences between the output values. Notice that they all equal 3. Since the second differences are the same, the degree of the polynomial is 2. This process only works when consecutive input values share a common difference. Part B. Since consecutive input values share a common difference of 3, we can analyze the differences between the output values to figure out the degree of polynomial g of x. The first differences are not equal, so g of x is not degree 1. The second differences are not the same either, so g of x is not degree 2. But the third differences are all negative 1, so this polynomial is degree 3. Now let's talk about even and odd functions. Functions can be classified as even, odd, or neither, depending on what type of symmetry they have. A function is considered even if it is symmetric about the y-axis, if the y-axis splits it right down the middle with a mirror image on both sides. So this function is even. A function is considered odd if it is symmetric about the origin. That means if I were to rotate this picture 180 degrees and turn it upside down, it would still look the same. I have copied this image so I can rotate. So here I go, rotate right 90 degrees, and let's rotate another 90 degrees. Okay, ignoring how the numbers look, do you see how the picture still looks the same? In fact, I guess I can just drag this off to the side to show you how these look identical. So that's what it means for a function to have odd symmetry. If you are given a polynomial function like f of x here, and you are asked to show that f of x is even, you will prove it algebraically using this rule. This is saying that a function is even if you plug in negative x and you get the same function back again after you simplify. For example, watch what happens if I evaluate f at negative x. Then this becomes negative x to the 4th power minus 8 times negative x squared plus 1. So f at negative x is equal to, when you raise an expression to an even power, the negative sign is going to go away. It's always going to be positive. So this is going to become just x to the 4th power without the negative sign. Raising this negative x to the 2nd power makes this negative sign go away. So I bring down my negative 8, but then it's simply x squared. And then I just bring down the plus 1. Notice that this polynomial is exactly the same as what we have here. In other words, f at negative x is equal to f at x. and that proves that f of x is even. If we were asked to justify our answer, we would say f of x is even because f at negative x equals f of x. On the other hand, if we are asked to show that a given polynomial is odd, we need to show that g at negative x is equal to the opposite of g of x. In other words, we need to show that if you plug in negative x, you get the opposite of the original function. For example, if we are asked to show that g of x is odd, we need to evaluate g at negative x, or simplify g at negative x. So this would be negative x to the third power minus 9 times negative x. So we have g at negative x equals. When you raise a negative number to an odd power, the negative does not go away. So I can take away the parentheses, but that negative will still be there. So this is going to be negative x to the third power. We don't have any exponent here. If there was one, it would just be this invisible 1. But anyway, we have a negative times a negative. So that's going to be a positive 9x when we write it without parentheses. Now, just to complete the proof, all right, remember we want to show that g at negative x equals the opposite of g of x. So let's factor out a negative sign, like a GCF. So we'll just keep bringing this down. So g at negative x equals. Let's bring out a negative sign outside of parentheses. So that changes the sign of everything you see here. So that's going to be x to the third power minus 9x. Notice that this is now g of x. In other words, g at negative x is equal to the opposite of g of x. If you are asked to justify your answer, say g of x is odd because g at negative x equals the opposite of g of x, just like this. I encourage you to pause the video and try example 7a on your own. Alright, I'm going to assume that you did that. So if I want to determine if these two polynomials are even, odd, or neither, we just plug in negative x. If we get the original function back again, then it's even. If we get the opposite of the original function, then it's odd. If we get neither one of those, then it's neither. So let's see what happens. If we do h at negative x, this is going to be 2 times negative x to the fourth power minus negative x squared, and then we have the plus 5. So we have h at negative x equals. Remember, an even power makes this negative go away. So I can rewrite this without parentheses by just writing 2x to the fourth power. Poof, it's gone. Alright, this negative in the front is not going anywhere. I'm just going to bring that down. But the negative inside the parentheses is going to go away because of the even power. So I have minus x squared. And then I just bring down the plus 5. This is exactly what you see right here. Therefore, h at negative x is equal to the original function h of x. So, h of x is even. Alright, how about b? Again, we plug in negative x. This is k. This is function k. So let's do k at negative x and see what happens. So this is going to be negative x to the third power plus 3 times negative x and then minus 1. So we have k at negative x equals. An odd exponent does not make the negative sign go away. So when I take away the parentheses, I will have negative x to the third power. This one doesn't have an exponent, so I can go ahead and multiply these together. A positive times a negative is a negative. So this is negative 3x. And then I'm just going to bring down the negative 1. Okay, because of the negative in the front, obviously the way it is, it does not equal the original function. So my only hope for a match is to try to factor out a negative 1. But if I do that, all right, k at negative x equals, okay, let's pull a negative outside of the parentheses. That's going to turn this into x to the third power plus 3x plus 1. This is so close to being the opposite of k of x, but not quite, because here I have a plus 1 and this is a minus 1. So k at negative x does not equal the original function, nor does it equal the opposite of the original function. We conclude by saying k at negative x does not equal k of x or the opposite of k of x. So k of x is neither even nor odd. So that is the formal way to do it. And if you are asked to show or prove that a given polynomial is even, odd, or neither, that's how you would do it. But if you are merely asked to determine if a polynomial is even, odd, or neither, then there's a shortcut, which I'm going to show you right now. A polynomial will be even if all the exponents are even. And guess what? A polynomial will be odd if all the exponents are odd. If you have a mixture of even exponents and odd exponents, then it's neither. To use this shortcut, I need you to be aware that 0 is an even number. And if you see a constant like 7, I want you to think of it as 7x to the 0 power. So that is an even exponent. Also, if you see an x without an exponent, it is x to the 1 power. So that counts as an odd exponent. So looking at example 7a again, we see the exponents are 4 and 2, and then this constant of 5, we will think of this as 5x to the 0 power, which is another even number. All of the exponents are even, so this polynomial is an even function. On the other hand, when we look at k of x, we see an odd exponent, the 3, and then this plain x is x to the 1 power. That's another odd. So we have odd, odd, but then this constant is x to the 0 power, and that's even. So we have odd, odd, even. A mixture of odd exponents and even exponents means k of x is neither even nor odd. That's the shortcut. Go ahead and glance at this graph for part C. Is this even, odd, or neither? Well, this is going to be odd symmetry. This is the one where if I were to rotate this 180 degrees around the origin, it would still look the same. So that is odd. What about D? D is neither even nor odd. It looks like it might be even. I can see some symmetry here, but the line of symmetry just is not the y-axis. The line of symmetry is the line x equals 1, and that does not count as an even function. It has to be symmetric about the y-axis, so this is neither even nor odd. Hey guys, don't forget to like and subscribe. But also, if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.